Welcome back. Let me share the screen. So we were discussing ordinary differential equations, and today we're gonna, no, we didn't start discussing it, but we will discuss today. Then we're gonna solve the hydrogen atom with using SkyP. So the ordinary differential equations have two types of implementations in SkyP. One is Odaint, which is so-called function-based interface, and the other one is Ode, which is more object-oriented interface. Both have equivalent functionality. It turns out that Ode offers a little bit more fine level of control, but for our purposes, Odaint is just good enough, and it's slightly easier to use because it's really just a function. So we're going to use this Odaint. So how does it work? Well, we need to, yeah, here is the description of function. So we need to give, as a first argument, this needs to be a function that gives the derivative of all independent, of all variables. So variables in general can be an array of functions y of t. So y1 of t, y2 of t to yn of t. You can have n components, isn't it? Because this is n dimensional first order differential equation. So any differential equation can always be turned into so-called standard form, and standard form is the one where you have n first order differential equations. And what we require in order to solve this this system of equations is that user gives the derivative of each component. Okay, so we need to specify the derivative for each component, which is some function f of y and t. Okay, so now this function f of y and t should be given as the first argument to Odaint. Then the second argument has to be the initial condition, which is the value of y at the beginning, when t is equal to first entry, like 0, for example. So when independent variable is t is like time, isn't it? We have t like time independent variable, and then we are solving for these functions y1 of t, y2 of t to yn of t as a function of time. And we need to give here initial condition, which is value of y for all components. And then t is the independent variable, which needs to be an array of numbers, which is just like mesh for the time variable. Now this mesh for the time variable needs to be fine enough so that the function can be, so that the solution is smooth. The point is that if the time variable is not, let's say, fine enough, not precise enough, so that the time distance is too big, then the solution will not be precise. Okay, because internally this system uses some Runge-Kutta method of the fourth order, which is reasonably precise, provided that the function does not change too abruptly within the time step that we give. Okay, so therefore, if you're concerned whether the solution is precise enough, you just need to use more points in the same time interval. Okay. Yeah. Now the good thing about this using this Odaint is, of course, we don't know the internal workings of Odaint, but as far as I know, it uses some type of Runge-Kutta method, which is a general purpose solver for the differential equation, which is precise up to the order 4. Okay, order 4. It's like Taylor expansion, which is not precise only to the first order or second order, but up to the order 4. So O of h to the 4, of h to the 5th, I think, is the error bar. So yeah, we were going to demonstrate this for two examples. One is going to be, the first one is going to be double pendulum, and the second will be damped harmonic oscillator. So two very common classical problem in physics. So first, double pendulum, which you can find on the internet, Wikipedia. So we display here the image from Wikipedia. So image is something that can take arbitrary URL from the internet and can display in our cell the picture from internet. That's convenient, so we don't need to have it locally stored. Well, here I stole the equations from the internet for double pendulum, which of course we're supposed to be able to derive that. So the independent variables, the dependent variables are the angle θ1, which is the angle for the upper pendulum. θ2 is the angle for the lower pendulum. Then the momentum associated with the first pendulum and the momentum associated with the second pendulum, isn't it? So this is derived in a standard way, so that the momentum is canonical variable to the angle. Okay, so these are the equations, which are pretty straightforward to derive. In order to make them slightly more appropriate for inputting to the computer, we're gonna combine them together into an array where the first component is the first angle, second component is the second angle, third component is P is the first momentum, and fourth component is the second momentum. Okay, so this is our X, and then we are gonna rewrite these four equations in terms of X. Again, this is just for convenience of coding later on. So we have the derivative of x1, derivative of x2, derivative of x3, and derivative of x4 is given by this expression. Okay, so now given all these expressions, we can then write our function. So we are basically specifying now this function, okay? This function, which is the derivative of all the components, okay? F of y and t. So the derivative, well, the function is basically just exactly that. Exactly, that's what we derived here. Okay, you see it? So we need to input this derivative, this function f, which takes as a first argument x and t. So in order to figure out how this function should look like, of course, we need to look at the documentation for the Odaint. So let's do help of Odaint. And it says that the first variable should be func, okay? And this func should be, it specifies what it needs to be. It's a callable function that has to have as a first argument y and the second argument t, where t is of course independent variable and y is the dependent variable, isn't it? And calculates the derivatives, okay? So our y is called x here. Yeah, so let me close this. Oops. Yeah, like this. So our y is here called x. I don't know why I chose x, and t is independent variable. And now we need to specify what is dx1, which is dx over dt, dx1 over dt, dx2 over dt, dx3 over dt, and dx4 over dt. And we need to return an array for all four components. So we get as an input array of four components. And in this line here, we unpack the four components. So we get an x, which is an array of four components, x1, x2, x3, x4. We unpack them. For convenience, we unpack them. We could, of course, just use here elements from X. And then we construct an array, which again has four components for the derivatives. Now, here I hard-coded what is G, 9.82, of course, and I chose the length and mass to be both equal to 1. That's just convenience. I mean, in the original version that probably you have from GitHub, this L and M are slightly different, but it doesn't matter. I changed them to 1 to be consistent with what we will have later on with in simulations. So of course, we could also add L and M as an input to dx, and then we will need to use args variable when we call Odaint, isn't it? So we did not need to hard code this. We could use this as an args to the Odaint outside, which is probably more convenient. But for simplicity, we wanted to hard code here, L and M. So, well, now these 4 lines are basically just literally coding these equations that come from Wikipedia for the double pendulum. Okay, and then we have to choose some initial conditions for our pendulum, and we need to specify what is the time mesh, the mesh for the independent variable. So we chose the initial condition, the first pendulum to be at pi over 4, and the second pendulum to be at pi over 2. So the second pendulum is 90 degrees. The first pendulum is 45 degrees, and both are at rest. We specified that the time variable goes from 0 to 10, and we will use only 250 points. Now this mesh is somewhat rough. It's not perfect, but it's okay. In simulations, we're going to use much more precise mesh later on. Now, the point is that if we are solving this differential equation for a long time, the error accumulates. So therefore, if this mesh is kind of too rough, after a substantial amount of time, we will see that the error tends to be bigger and bigger and bigger. Okay, and that's hard to avoid actually. I mean, for solution of hydrogen atom, we will realize how to tweak the system to make the solution more precise. So we are gonna integrate from infinity down to 0 rather than from 0 up to infinity. So we're gonna use this usual trick of turning around the iteration. But in the double pendulum, I don't know of a trick. I mean, this forward integration is reasonably stable, provided that you have a sufficient number of points. But I don't know of a good trick of how to make it even more stable. Okay, but double pendulum is known to be chaotic. It's a chaotic system. So therefore, sooner or later, if you integrate this thing for a long enough time, then the solution is gonna be extremely sensitive to initial conditions. You know, whenever you have a chaos, then we know that a tiny change in the initial conditions, or even the errors of the integration, will result in completely different solution after a long time. Okay, so you can't avoid this problem when the system is chaotic. So the final result in a chaotic regime is infinitely sensitive to either a change of the initial condition or to any errors that you might accumulate during integration. Okay, nevertheless, we can still get a reasonable approximation for the time difference, for the time dependence of double pendulum, and you will see that it looks pretty, the solution looks pretty physical, pretty good. Okay, so we're going to use now 250 points distributed between 0 and 10. And then all you need to do is to execute Odaint. So did I execute this? I didn't yet. Okay, so we execute Odaint. Where the first argument is this function dx, then the second is our initial condition, and the third is the independent variable t. Okay, so we check documentation, and that's exactly what documentation was telling us. That's how we need to call Odaint, and this can be written into our final solution x, which gives all 4 components as a function of time. This is the the first angle, the second angle, the first momentum, and the second momentum. Okay, so by executing this, we basically solved the differential equation for all times that are given in this mesh T. Okay, all times are now solved. Now here we are going to just plot the solution in 2D plots. Okay, to get some familiarity with the solution. So what we're going to do here, I decided to use in this example more object-oriented plotting. Okay, it's slightly different than what we used before. We are going to use so-called, so we still use PLT, which is Matplotlib PyLab, but we're going to use subplot routine, which subplots, which gives, which can plot several plots on the same figure. Okay, so in this case, we want to plot two figures next to each other. Okay, this is called 1 by 2. So it's one row and two columns. In general, you can specify here n, m, any integer times any integer, which will create n rows, m and m column subplots. Okay, so you have lots of possibilities, and this subplots returns. Yeah, we also specify here fig size 12 times 4. This is slightly bigger fig size than default. I think default is 6.4 and 6.4 and 4.4 or something like that. So we specify a little bigger figure so that it fits nicely into the cell here. Now, one thing which I wanted to explain is that this subplots returns axis, and then we have to use axis for plotting, for actually throwing plots into the screen. And we have two axes because we specified here 1, 2. So basically there are two plots. We specify here that we're going to be two subplots. Therefore, we have axis of 0 and axis of 1. And so something is going to be plotted in axis of 0 and something is going to be plotted on axis of 1. Okay. Now, I wanted to confuse you a little bit here so that you're not too confident into how to use subplots. It turns out that there are many different variants of how to use subplots, and it is confusing a little bit. So I have here, I opened here a page where the syntax is explained. And you can see that there are many ways of producing the same plot. Yeah, I also get confused many times. So right now we are using this one, PLT subplots, okay, which gives you two arguments, which is figure and axis. And then later on, we're going to do something with axis, okay? In addition to this, the alternative is to use command PLT figure first, which gives you only figure. And then later on, you specify fig.add subplots to get axis, okay? Or you can use fig subplots where you can specify how many, like 3 times 5, 3 and 5, which will give you several subplots, okay? And you can also have another routine which is called add axis, in which you specify the distance from the left, from the bottom, and the width and the height, if you want to. So fine control of these subplots. So this is the third way to do it. And similarly, in this alternative way, where you get figure and axis at the same time, you can also use subplots, subplot, and also axis, where you give this left, bottom, width, and height. So many ways of how to produce a subplot. Therefore, yeah, I mean, any of them is good enough. Any of them will work. But unfortunately, the codes vary a lot. Yeah, from code to code. Okay, so here we use subplots, which produces 2 axes, not just 1, but 2 axes, because we have this 1 times 2. And then on the first axis, we're going to plot on vertical on horizontal axis, we're going to plot time, and on vertical axis we're going to plot the first column, which is basically our theta 1, isn't it? Then we're going to also plot theta 2, which is the second column, and in addition we are going to add here legend so that this label theta 1 and theta 2 is going to be displayed. If we don't write this legend, lock is best, then theta 1 and theta 2 will not be displayed. And then finally, we're going to write, we're going to add the X label here, time. Okay. So if we execute this, so what do we get? We get, this is the first plot, which plots, you see theta 1 here. So theta 1 is a function of time. So it's the column 0, and it has this legend, theta 1, theta 2, and X label is added here on the bottom as a time. Now the second plot that we want to do is specify, calculate x1, y1, x2, and y2, and we want to plot all of those in XY plot. Okay, so XY plot. So this doesn't specify how this changes as a function of time, but just show you the entire contour that both pendulums make. So the first pendulum here, basically, you see that doesn't returns more or less all the time back to its original position. So it doesn't, this thing doesn't widen a lot, which means that it's relatively stable trajectory. But the second pendulum has much less stable trajectory, isn't it? It's doing all kinds of strange wiggles. Okay, so yeah, so the first one is almost periodic, and the second one is definitely quite different from periodicity. Of course, if we zoom in the first one, we will also see that it's not periodic, not really periodic, but at first sight it looks much more periodic than the second one. Okay, so now on the second pendulum, we're gonna, in second plot, we're gonna plot x1, y1, x2, y2. Okay, and then we're gonna set the x limit and y limit so that all the data is nicely displayed. So here the y limit goes from -1 to 0, and the x limit goes from -1 to 1. Yeah, I wonder why it's 1 to -1. Aha, it was flipped. I guess more natural would be -1 to 1. I don't know. Why did they write 1 to 1 as 1? Okay, so this, I guess, is more natural. Okay, so this is the plot. Now, it gives you some feeling of how the double pendulum solution looks like. But of course, it's not the same as seeing a real animation for the double pendulum, isn't it? And the interesting thing is that the matplotlib supports animation. Okay, and we would like to show in real life how the pendulum behaves. I have provided you a code which is called pendulum.py, and we can execute it and actually see the animation. Now, this is done outside this Jupyter, because somehow I was not able to make Jupyter simulation work, or I was not able to make the simulation work inside Jupyter. I don't know. It seems that there are some issues that I was not able to resolve. If some of you figure out what to do exactly, I would be grateful. But for now, we're going to use standard Python code, so standard Python module, we're going to create Python module which will produce a simulation. Okay. Any questions? No questions up to now. Okay. So the question is, how do we make the simulation for the double pendulum? So what to do? Well, here's the code. Whoops. So what I've done here is I copied most of the code from Jupyter. So I made G, L, and M global variables here, but otherwise I copied literally this dx, which is the derivative of well, the function that we need for solving Odaint. I used this called Numba acceleration in this case, because this function clearly is Numba acceleratable. It doesn't have any unusual types such as dictionaries. So therefore, this Numba should accelerate this function very well. Then for the independent variable t, I chose slightly longer times, 20, so that simulation kind of takes a little bit more time, that looks a bit more realistic. It doesn't end so quickly. And then I use slightly more points. Instead of 250, I used 800 points. So a little bit more precise time step. This more precise time step means the solution is going to be more precise, or the error will accumulate much slower. Okay, so later on down there, we're going to need the time step dt. This is just in order to print what is the time, current time. So therefore, we need the difference between what is the size of time step. Okay, then initial state we used before pi over 4, pi over 2. But it turns out that pi over 4, pi over 2 is kind of boring for simulation. We can try, but you will see that it's boring. Pi over 4, pi over 2, 0, 0, like this. It kind of doesn't do much. So therefore, oops, I decided to choose a little bit more exotic state. Yeah. So this one kind of doesn't do much over time. The kinetic energy is too small. It doesn't wind around. And so I think this is still pretty far from chaotic regime. But once you give sufficient energy at the beginning, then the pendulum starts to behave chaotic, and it's kind of more fun to watch. Okay, so to give pendulum a little bit higher kinetic energy, it's a good idea to increase this initial angles and make the second angle actually opposite to the first one. So as you can see at the beginning, this has literally a lot of kinetic energy. So it immediately starts to wind around, and the behavior is much more non-trivial. Okay, so this is the initial condition. And then we do the same thing that before. We do Odaint with this function dx, initial condition, and time step. Okay, so up to now, we just repeated exactly the same that we had in Jupyter. And then we also calculate here x1, y1, x2, y2, which are simply given once you have the first angle and the second angle. You can of course calculate very easily the position of both pendulums as that. So the first pendulum has position, no, the x position of the first pendulum is sine x times L. The y position of the first pendulum is minus L cosine x, and so on. And x2 is x1 plus sine x of the second angle, and so on and so forth. So this is pretty straightforward. Position of both pendula. And so up to here, we just have a copy from Jupyter. And now the simulation or animation is this stuff down there. Okay, so this is the animation. That's what I wanted to explain. Okay, so how is the animation done? Well, the most important function here is animation func animation. Okay, so animation func animation. So how do we get this animation func animation? Well, this animation is part of matplotlib animation. So matplotlib has not only plotting routines, but it also has animation routines. So we need to import from matplotlib animation. Import matplotlib animation as animation means that from now on we can use anything from matplotlib animation as animation dot something. And in particular, the function that we're interested in is func animation that uses several functions. So let me check documentation for this function. Import matplotlib animation as animation, and then we are going to say animation func animation help animation func animation. Now I can explain. So this func animation needs to get, first it needs to be figure, then it has to be function, then it has to be number of frames, init function, and many other functions, many other things possible. It's possible to specify. So let's go slowly. So first we need to give figure. So what is figure? Well, figure is just a figure that we create with matplotlib functions, with matplotlib subplot routine. So here I decided to use exactly the same functions that we use in Jupyter. So let me show you the Jupyter thing. Here we use fig and axis were obtained by plot subplots and specifying fig size and so on. So we're going to use the same command. The only difference here is that we need only one plot, 1 times 1. We don't need 2 by 4, 1 by 2, but only one subplot. Isn't that because there's only one plot that we need? So we're gonna call PLT subplot. We are not going to specify fig size because we're going to use default fig size. And this gives you figure. And in this case, it gives you just one axis, not more than one. Okay. Because if we specify just 1 by 1, it will give you only one axis, not an array of axes. Okay, as before. So we have our axis. Then this is useful. Actually, we specify the range for the axis. Basically, that it goes from -2L to 2L. The x and y go both from -2L to 2L. So at the beginning, we specify fixed fixed size for the plot. Okay. Why is that important? Because when we animate, we don't want the plot to dynamically change, or we don't want it to be too small. But we want this to be big enough so that both pendulum fit into the animation, and we want to fix it at the very beginning. So we are fixing the size of the display. Okay. And 2L is enough, isn't it? So in all directions, if we have all directions 2L, then this will definitely fit to both pendula. Pendula will never be able to escape out of the figure. Okay, so for convenience, we add here grid, but that's not essential. Yeah, so here it's a bit confusing thing. We can, of course, achieve exactly the same plot, exactly the same thing here with the different syntax, which I explained before. In addition to using subplots, we can use PLT figure first to get figure, and then we can use add subplot on figure in order to get axis. Okay, so this is so-called two-stage process rather than one-stage process here, but it has an advantage in this case, because if you use this add subplot command, then you can specify directly x limit and y limit inside this function call. But again, not a big deal here. We are adding this x limit and y limit after we initialize figure. So equivalent way of doing it. Then Next, what we do is we create a plot. We actually plot, create an empty plot, okay? An empty plot in which we specify that the width of this pendulum is going to be 2. So we're going to make this, this line a little bit thicker so that we see where the pendulum is. So this is the thickness of the line. And then we're going to make sure that at the end of the line, there is going to be a symbol, which is this O here means symbol is a circle. So the symbol the pendulum will end with a circle, okay? And this minus means that it's going to be a circle plus a line. O minus means circle plus a line, okay? So, but for now, we are not plotting the pendulum yet. In principle, we could plot the pendulum with initial conditions if we wanted to, but we don't need to, because this animation routine, which will update the plot, will actually start to plot position from the first position on. So we can just put for now completely empty plot if you want to. Then this time template is just the string which is going to be thrown onto the plot, and then we add text at particular position in the plot. At x is 0.05 and y is 0.9. Currently, this text is empty, but this is just we're just creating a holder on which we're going to throw later on objects. So we created time text and we created a line. So with this plot, we created an object line and an object time text, which are going to be changed inside animation routine. Okay. So this animation routine here, you see line will be updated. So here we created a line. Oops. We created a line with the plot routine, and later on we're going to update line inside animation. And we also created this time text, and we are going to update the time text inside animation routine. Okay, so that's the idea. Okay, so once we have this empty line or placeholder for the line, and we have placeholder for the text, then we need to specify the crucial routine, which is called animate. Okay, it doesn't matter what name you give, but it has to be a routine which actually updates the plot for every time frame. Okay, and we need to specify here how many time frames we have altogether. And well, the number of time frames here is of course as much as the length of the independent variable t. Okay, so we have as many as the number of this is an array which is up to the length of the independent variable t. So that's how many frames we have. And we need this function animate, which actually updates the figure for every independent variable t. So what does it do? Well, it's actually quite simple. This animate takes only one argument, which is the index to the frame. So this I goes between 0, 1, 2, 3, 4 up to the n-1, where n is the number of frames. So basically with this A range here, we specified how many frames we have altogether. And then this animate is called by this integers that are given here as the third argument. So we're going to give we are given an array 0, 1, 2, 3 up to n-1, and then this I will be changing from 0, 1, 2, 3 to n-1. Okay. Now, if we are given an index I, then we need to be able to update the figure. So what do we need to do? Well, it's quite easy. The x, basically to plot both pendulum, we need to have a line from 0 to x1 and then from x1 to x2, this is the x component for the two lines, and then the y component for the two lines is 0, y1, and y2, isn't it? So this is x for this particular line, and this is y for this particular line. Okay, these are the two pendulums, and then all we need to do is to update our line that was specified here. So at the in the top, we we got handle to the line by using plot, and now all we need to do is to update it with the current configuration at time ti, isn't it? At this time step, at this frame of I. So we just need to update the line. So the updating of the line is done by calling member function set data. So line has a function which is called set data, and we update it. And similarly, we need to update the text with set text, and then set text, we need to put some text in there, and our text is going to be time template, which in this case is time is equal to %1. So it means that we are going to specify the precision to 1 digit, and this is going to be floating point number, which is I times dt. We needed this dt, this timestamp, in order to calculate from the index to the time frame. We want to know what is the time. Okay, so we're going to specify here the time, and now let me run this again, and you're going to see once more what happens. So you see this time here, time that is changing, isn't it? On the top left, this is specified through this set text. Okay, we are updating time as we go. Time is 6.97 and so on, with precision only one after the dot, one figure after the dot, because of this 0, 1 here. And what else? Yeah, so this animate is of course the crucial routine. Animate is doing, animate is doing all the work. Okay. Yeah, the only thing that we need to do at the end is this invoke plot show. Now, this works, of course. Now, this is not the most efficient way of doing it. There is a little bit more efficient way of doing it. Namely, animate allows one to use blit is false or blit is true. So what is this blit? Well, according to documentation, blit is something that can use, if you have a simulation where a lot of things don't change from step to step, you can update only things that were changed rather than everything. So rather than replotting the entire plot, you can only update things that were changed. Now, when blit is equal to false, it means that we are not updating, we are just always displaying the new plot. Okay, this is a little bit inefficient, especially when you have complicated backgrounds on many things move. Okay, then blit is false is not a good idea. Okay, so in this case, we want to do blit is true. Okay, blit is true. But if we do blit is true, now unfortunately our simulation doesn't work yet. Okay, doesn't work. Why? Well, because when blit is equal to true, our functions need to be slightly more complicated. So in addition to our function animate, we also need to have an init function. And init function need to specify which data or which components of the plot are going to be changed with animation. Okay, what is going to be updated? Okay, so this init function here that was specified, init function is init. Whenever blit was false, that was actually not needed. Like we could remove it, but I kept it there. So for the case of blit is true. So when blit is equal to true, we need to specify init function, okay, which needs to return the objects that are going to be changed during simulation. So in this case, we're going to return two objects, which is line and the text. These are the two objects that are going to be changed. We need to return them. Okay. It doesn't matter really how they look like right now. All we need to do is to return an example of this line and text that is going to be updated. Okay. So we need to have a proper initialization routine, and then the animation routine also need to return the objects which were changed. Okay, so it needs to return the line and time text for this particular configuration, this particular time step I, isn't it? Now, when both of those init and animate are properly updated, then blit is true should also work. Yeah, and you see this one is somewhat more efficient than blit is false, because it does not replot everything, but replots only things that were changed. Yeah. Now, in terms of being realistic, when you simulate something like that, you have to kind of guess that you have to display the frames with the proper speed. So right now you see that this time is changing roughly realistically, in the sense that when the time becomes 1 second, it's roughly 1 second in time, roughly 1 second. So how to tune this? Well, you have to specify this interval here, this variable. So interval is delay between frames in milliseconds. So default is 200. So of course, if you specify 200, this is going to look extremely non-realistic, isn't it? Because, well, the time is changing way too slowly, isn't it? Slow motion. So, but for our case, 20 is good enough. But of course, if we make this much smaller, then the pendulum will go extremely fast, isn't it? Yeah. Okay. So this demonstrates how to animate such a solution of a classical system, which you can plot the trajectory. Okay. Any question up to now? Any question? None? Do you have this plot? I guess you have, huh? From GitHub, you were able to obtain. The plot from the GitHub is slightly different because I edited it a little bit, but it's very similar. So I edited a few things today so that it's more compatible with the Jupyter equivalent. Okay, so with this we finished this pendulum problem. So we still want to show one more example of using Odaint routine on the damped harmonic oscillator, and then we're going to use Fourier transform on the damped harmonic oscillator, because that's a good example of how to use Fourier transformation. And then we just have optimization left, and basically this is all about SkyPy routines. Okay, so let's look at another example for using Odaint. Damped harmonic oscillator has, in addition to the second derivative with respect to t, it has this term 2 psi omega 0, the damping term. And we need to turn the second order differential equation into two first order differential equations in order to code this, isn't it? And we're going to do this by choosing momentum, which is dx over dt, and then we can specify we can have as a two component x and p, and we need to specify then dp over dt in dx over dt, isn't it? So this constitutes the two first order differential equations that we need to solve. So we're going to specify now our solution of the damp harmonic oscillator dy. And remember, the first two variables are fixed. You cannot change them. The first variable has to be the components for the dependent variables, which is now called y. And then the second variable has to be an independent variable, which is called t, time, isn't it? So these two, the first two are fixed, no freedom. And here we decided to add some extra arguments, zeta and omega 0. This is our choice. So before we did not do that, we hard coded. So here you see dx had only two variables, x and t, and we decided to hard code L and M, okay? But of course we could also give here L and M as extra arguments, and then we would need to use the so-called arcs in the Odaint, okay? But here we didn't. But in harmonic oscillator, we decided to add here the two extra variables, zeta and W0, to demonstrate how to specify those variables in later on in when we call this function. Okay. So once we have y, t, zeta, and W0, what we do again is unpack y into x and p. Of course, we don't need to specify y0, y1, so we could just do this. This is good enough. So y is first unpacked into the x and p, and then we write that dx is, of course, p, and dp is minus 2 zeta omega 0. So I'm reading this this differential equation, and I'm coding it here: minus 2 zeta w0 times p minus omega 0 squared times x, isn't it? So this code is exactly equivalent to this this equation for damp harmonic oscillator, and then we return the derivatives. Now the important point is the derivatives have to be given in the same order as dependent variables, isn't it? Y is given in x first and then momentum, so we need to give the derivative of x first and then derivative of momentum. So this is our dy. Of course, we should actually return here the array, but if we don't return the array, it's okay, because it's going to be done on the fly. So we're going to return the list, but list is kind of converted into array when needed. So basically this array here is not essential. Okay, then what we do is we use Odaint, isn't it, like this? We need, of course, this derivative that we just specified, dy. We need initial condition, and we need independent variable t, and then an extra arguments if need be. Okay, so initial condition, y0. Well, we will specify initial condition here, which is what the position is 1 and the momentum is 0, for example. That's a reasonable starting point. Then the time variable, it's going to, I decided that it's going to go from 0 to 10 with 1,000 points in between. So again, 1,000 points means that we kind of create a very fine mesh so that the solution will look, the solution is going to be pretty precise. And then I decided here that my frequency is going to be 2 pi times 1, so 2 pi, so that the units are very nice. Okay, so we now solve this damp harmonic oscillator for four different damping parameters. So here we can specify these arcs, and arcs, as you remember last time, specifies the extra arguments that this function dy needs. Okay, this function dy here needs two extra variables, zeta and w0, and these two are specified when we call Odaint. Okay, You remember this syntax the last time that we discussed. So this arcs now changes zeta. So zeta for this case is 0. Zeta for the second case is 0.2, which is typical under-damped harmonic oscillator. Then zeta for third case is 1, which is the exactly critical damping. When zeta is 1 in terms of frequency being 2 pi times 1, then the damping is critical. And if zeta is bigger than 1, we have an overdamped case, overdamped harmonic oscillator. Okay, so
Professor? Professor?
Yes.
I have a question. When you're doing y1, y2, y3, y4, everything after dy, those are all arguments for dy, right? I know the args, I get that, but y0 and yt, I'm just curious, why the comma and not parentheses, like typically?
Which comma you mean? Here, this comma?
No, the one after dy. Why not dy parentheses and then your arguments?
Well, because you're not allowed to give this. So here you need to give a function. Okay, you need to give a function. You should not evaluate the function. You should give a pointer to a function. That's how you have to think of it. Okay, so this thing, the first argument requires you to give the name of the function and nothing else, not call the function, because function is going to be called inside Odaint. Okay, so in some sense, Odaint just requires you to give a pointer where this function is. Okay, that's all. Okay, and then of course you cannot give easily extra parameters. I mean, in C, this is very hard. You have to create a functor, another class. It's complicated if you want to do this in C. Okay, so but Python provides this nice functionality that basically you can give extra arguments through this arcs trick. Okay, if you want to do something similar in C, it's really complicated. You have to create a new class which is called functor, then give these extra arguments into the class somehow in its initialization state, for example, and then use the functor instead of the function itself.
But that distinction of using dy as a pointer here, and then the following values would be arguments for dy, is that written into ODE-int?
Sorry, does that?
Is that written into ODE-int? Like ODE-int is expecting its arguments to come in this form. First one being the pointer, then the rest. Absolutely.
So let me demonstrate this once more. From Skype import integrate help integrate Odaint. Okay, so once more, we have function, isn't it? And this function requires callable. So you see, it has to be callable. It has to be a callable function. Okay, and the specification for this function is that it has to have two variables. It takes two variables, which is y and t, and then the rest are optional arguments. Okay, optional arguments. And these optional arguments, of course, can always be given through arcs. Where is the arcs? Arcs here, arcs. And then it will explain arcs is tuple optional extra arguments to pass to function. Okay, so that's how all Skype routines are similar in the sense that arcs always means extra arguments that can be passed to a function. This is very, very standard. So it's not just for this routine, but almost all routines in Skype. Function has to have this form. In other words, the first argument is y, the second argument is t, and then optional, which can be given through arcs. Okay. And once more, the first argument has to be a function, which is kind of a pointer to a function, or basically the name of the function. You cannot call the function here. It has to be function dy. Okay, so when we evaluate this, we get 4 different solutions for the harmonic oscillator: undamped, underdamped, critical damped, overdamped, and then we can plot those. Now, this time I'm using the simplest possible plot because we have just one. We just want to create one plot, no subplots, no complicated things. So we're going to just invoke a plot routine, PLT plot, and we're going to plot all 4 cases. So we are taking only the first column because the first column is actually the position of the position X. The second column is momentum P. So we don't want to look at momentum. We're going to just want to look at the position. So we'll look at the position for the undamped oscillator, position for the underdamped, position for the critical damped, and for position for the overdamped. And here we also add a label for all these cases so that we can see on the plot which one is which. And as expected, the undamped is just usual sinusoidal sinusoidal plot. Then underdamped oscillates a little bit and quickly, exponentially, of course, is damped out. Then critical damped, as is well known, it follows the sinusoidal curve for a very short period of time, but then it clearly just falls off exponentially. And then finally, overdamped is the one that falls off extremely slowly, much slower than the original sinusoidal curve. So these are well-known solutions of the harmonic oscillator. Now the reason that we produce this is because it's convenient now to look at the Fourier components of those functions. So Fourier component of the sinusoidal function, of course, is a delta function, has only one frequency, isn't it? But if you have a damped harmonic oscillator, then it should have a distribution of frequencies, not just one, but has to have more than one frequency, isn't it? Because the Fourier transform has to give you the frequency has to change. Okay, so how do we do Fourier transform? Well, as you all know, as you probably well know, the most efficient way of doing Fourier transform is a so-called fast Fourier transform that does this in time not n square but n log n, which is way faster than n square. And this is implemented in so-called FFT-PEC routine. Okay, FFT-PEC, which is a library written in Fortran from netlib. So netlib is a repository of well-known old Fortran routines that are well efficiently implementing various numerical algorithms. So what we need to do here is we need to import from Skype FFT-PEC. We're going to import everything, but FFT-PEC includes this fast Fourier transform. And in addition, we are also going to use FFT frequency from NumPy FFT. Now, this second one is not essential, but it's convenient. Why? Because, well, fast Fourier transform doesn't give you the values of frequencies. So you need to kind of calculate yourself what the frequencies are. Basically, you give an array of data, and then you're given back frequencies for your data. And these frequencies are basically distributed in a linear mesh. And you as a user need to know what are the units of these frequencies. Now, for convenience, of course, NumPy has a routine which you can very easily get the values for the frequency. So we'll see this in a second. So so how do we do the fast Fourier transform? Well, we just take our variable such as y2. So what is y2? let me go back, y2 is underdamped harmonic oscillator. So we take our value for y2 for underdamped, for position of the underdamped harmonic oscillator, and then we just give this to FFT. That's it. FFT is a function inside Skype FFT pack. Okay, and this F now has a spectrum of frequencies for, it's an array, of course, which specifies spectrum of typical frequencies. Now, the unfortunate thing is that this is just an array, and we don't know what the first element, the second element, and the third element correspond to. What is the actual frequency in units of this time that we are giving. So in order to calculate what are the actual frequencies that correspond to our time variable for which we Fourier transform, we need to give here the time step t1 minus t0, and the number of the components in the time array. Okay, so the reason that this is so simple is because fast Fourier transform requires from us linear mesh. So we know that the time stamp, the time axis is uniformly distributed. Okay, so it has to be always uniformly distributed mesh. So the frequencies are also uniformly distributed. But of course, the exact values here are somewhat, well, the standard. One can look up how exactly they're given, but it's convenient to use FFT frequency routine, which returns us the exact frequencies that are going to use in this fast Fourier transform. Okay, so once we are given the frequencies and the specter, so for each frequency we know how much weight there is in the Fourier transform, isn't it? F is the weight in the Fourier transform, and W are the frequencies, and then we can display that, and we get this nice plot here, which shows you that well, frequencies around 1 actually are the most common. Okay, why? Because our harmonic oscillator has frequency 1 in these units. So if we use, for example, y1, which is undamped, this should be a delta function. I'm curious whether it works. Yeah. So y1 has a delta function, has only one frequency, isn't it? Only one frequency. And y2 has, of course, a continuous of frequencies. And y3 is then critical damped. And this has the distribution which peaks at 0. Okay, so the most interesting thing, of course, is y2, because this is kind of this is underdamped. Yeah, so it's still very clear that there is one specific frequency which is the most clear, the most contained. Now, we know that the signal is real, therefore the spectrum has to be symmetric. Okay, so positive and negative frequency in Fourier transform have to appear with exactly the same weight. Therefore, we actually need to plot only the positive frequencies, because there is no extra information hidden in negative frequencies. So therefore, we can cut out, if we want to, cut out only those data which corresponds to positive frequencies. So how do we do that? Well, we can use this fancy indices that we discovered last time in this NumPy lecture. So we can use where frequency is positive. Well, there is one thing that I want to point out here. When we plot this, look that there is this weird blue line on the bottom. Do you see it? Now, this blue line on the bottom turns out is the result of the fact that this frequencies W W's are not given in increasing order. So let me show you. If we look at the W starts with 0 and then goes to maximum, which is something like 50, yes, 49.85. And then it jumps back to minus 49.95 and goes back to small value, close to 0. Okay, so again, this mesh is linear, but it's given in a weird order. So it starts with 0, goes to maximum, then jumps back to minus omega over 2, and then back to 0. Now, why is this given in such a weird way? Well, because fast Fourier transform gives the data in this strange way. Okay, it turns out that fast Fourier transform gives the data first those that correspond to 0 frequency, then those that corresponds to the smallest frequency, next smallest frequency, and so on to maximum, and then it starts to go to negative and back. Okay, so therefore it's convenient to use this FFT frequency. Otherwise, we need to calculate this particular frequencies by hand. Now, the point is, because this X variable is given in such a strange way that it starts from 0, then goes to a large positive value, then goes back to negative value and back to 0. Therefore, this plot looks a bit funny. So it has this line on the bottom. Okay, it's consequences of this mesh, which is not constantly increasing, uniformly increasing. So in order to kind of improve this plot, what we should do is you should take only the positive frequencies out. Okay, all the negative frequencies that are specified in the second part of the data are useless for us. So now how to do that? Well, we can use this routine where, because where W is bigger than 0 will give you all the indices where the frequencies are positive, and then we can use this fancy indexing. You remember this from last time? Fancy indexing gives you only the components that we're actually interested in. This could also be done through the mask. This is more or less like the mask, but using indices. So this gives you the positive frequencies, and then we can plot only the positive frequencies. And we can see now that, okay, I can give you this so it doesn't plot anything. So only positive frequency. And now you see a nicer plot. It's very clearly peaked at 1. Well, it extends pretty far out. Yeah, but the frequencies bigger than 3, for example, are very, very uncommon, or very small, have very small weight. Yeah, so this is all about fast Fourier transform. So from now on, you can fast Fourier transform anything you want, isn't it? It's really pretty straightforward. Again, there are only 2 routines that you need to remember. One is FFT that gives you data in some strange order. And then if you want to know in what order you get this data, you need to call FFT freq routine from NumPy FFT. Okay, so with this, you can get all the necessary information. Okay, so we have one more thing to cover, which is optimization, and then we are done with SciPy. Yeah, only optimization, no optimization and interpolation. So what is optimization? Well, optimization contains 2 things. One is the finding of the minima or maxima, and the second one is finding roots. And both are, of course, very, very important in numerics. And finding roots is, of course, even more common than finding minima. But nevertheless, finding global minima of a multi-dimensional function is also a very complicated challenge. Unfortunately, we do not have a common routine that can always work. So there are literally tens or maybe hundreds of routines, and many of them are implemented in SkyPy, so that's a good thing. The problem, however, or the complicated part, is that you need to be able to find the routine which will work for your particular case. Okay, and finding global minimum in a complicated landscape of function is still a very complicated problem. Actually, some of them are NP complex, so not easy to solve. And for example, solving the Ising model is equivalent to solving a global minimum problem for the free energy, isn't it? But right now we are just interested in finding simple minima of relatively simple functions. So let's say we have just one-dimensional function, some polynomial, 4x to the 3, x minus 2 squared plus x to the 4, and then we plot this polynomial function, and we see that it has well-developed minima between -2 and -3, and between 0 and 1. And let's say we want to find the two minima. Okay, so what can we use? Well, fmin BFGS is one of the most powerful minimization routines that can solve multidimensional problems. So this is something that will probably work for most cases that you will need. Let me go into the documentation. Just a second, where is not this one? Oh, that's interesting. Yeah, so I wanted to show you, here, fmin BFGS. So this routine is actually called quasi-Newton method of Broyden, Fetcher, Goldbar, and Shano. Okay, so it's a pretty complex routine that was published here in 1999. It has this specification. So it definitely works for multi-dimensional problem. If I remember, f still needs to be a scalar variable. So it has to give you, function f needs to give you a number, and for which you are looking for a minimum. But this x here can be can have a arbitrary number of components. So in other words, this can be not one-dimensional, but can be n-dimensional function. Okay, that's pretty powerful. So optimization of n-dimensional function is a non-trivial problem, but this thing works pretty well in most cases. Okay, so most cases. The only difference between one-dimensional and n-dimensional case is that x becomes a vector. Okay, otherwise it's the same as one-dimensional case. Okay, so we're going to do, of course, one-dimensional optimization. We're going to give here function f as the first argument. So the first one here is f, and then x0 is the starting point, is our first approximation for the minimum, and then the system goes with quasi-Newton method, tries to find close minimum, close to that. So because our function is one-dimensional, we just need to give a number. If f was multidimensional function, we would need to give an array of numbers. Okay, but in this case, only one number is fine. And well, this minimum is found very quickly. The minimum, which is closer to -2, is at -2.67. So we can look at here. Yes, indeed, there is a minimum here. Then if we use the same function and we start with a minimum around 0.5, we will find another minimum, which is at 0.469 and so on. Okay, and we see that function evaluations that were needed is only 16 in this case, only 10 in this case. So relatively fastly approaching the minimum.
Professor?
Yes.
So, so we had to give two sets of values to find the two different minima, right?
Correct.
So, but if I were to give the entire landscape, and if it starts off somewhere on the positive side, it's only going to find one minimum, not the true minimum.
Correct. I mean, these routines can only find local minima. So all those routines are typically designed to go so-called downhill, and we always end up, most likely it will end up in the closest local minima, although it is not guaranteed that they will find the closest local minima. It's not even guaranteed, but they will find a minima. If you want to find the global minimum, you probably need something like a Monte Carlo method. Well, in one-dimensional case, it's easy. I mean, you just start with enough different cases, and then you compare them. But I mean, when you have multidimensional case, you will probably need Monte Carlo. So this is something that we're gonna work when we do the Ising model. We're gonna look for global minima of the system. Classical Monte Carlo. Yeah. Okay, so this F-mean BFGS is of course too powerful method. It's a canon for a BERT. So there are much simpler routines for one-dimensional interpolation. So Brent is one of them. So Brent basically works only on one-dimensional, optimizing one-dimensional routines. And of course, you have to give them the brackets. For example, we are looking for minimum in between 1 and 2, and it will find you the particular minimum. And then F-mean bound. The F-mean bound is a little bit more generic in the sense that it can search for multidimensional case, but you still need to give brackets in which you are searching for the minimum.
Professor?
Yes?
Are those just equivalent notations?
No, these are different routines. So I guess some of them are here found. Yeah. So for example, this one is F-mean bound, and the previous one was F-mean BFG. There are indeed different algorithms. So this one is minimize scalar, so interface to minimization algorithm for scalar univariate functions. So what does it use? It uses Brent's method. Okay, Brent's method of bracketing the interval. So it's really a different algorithm, Brent's algorithm. It's kind of quasi-Newton as well, as far as I remember, but it uses some extrapolation and some combination with Newton's method and so on. I don't know, or I wouldn't remember the details of this. And this one, F-mean BFG again is kind of fancy algorithm by these 4 people that are specified here. They all use some type of ideas of Newton and some type of extrapolations, but I wouldn't know the details.
So for F-min bound, then you're giving that range. It's just to keep computing until it finds the lowest value.
So you give the range, and then you don't allow the minimization routine to go outside this range. And if it doesn't find anything in there, it will say, sorry, no minima. The other one, you just go downhill and you find the first minima that can be found. It might be in infinity. Yeah, so it's a different algorithm. Yeah. Now, which one to use in your particular case? It's a non-trivial question, of course. I mean, if the function is simple, it doesn't matter which one you use. All of them will work. But when you have a complicated landscape, then it's absolutely unclear which one is more efficient. And that's something that, well, the good thing is that you have this all these Skype routines implemented, and you can just try which one is better. That's probably the best way. And hopefully several of them give you the same result, but one of them is faster. Okay. I actually, it's already 6:24. So is there any urgent question for today? Okay, so everything is too simple. Good. Well, if there are no questions, then see you next time, Wednesday.
Thanks, Professor.
Goodbye. Have a nice day.
See you.
See you.